inertial unit. So we consider here a vehicle. It can be, for instance, an underwater submarine, or it can be a plane or a car or whatever. And for this vehicle, we associate a frame. So here K1 directed to the bottom, A1, and on its right J1. So we know that we can go from the absolute frame to R1, the frame of the vehicle, by a rotation matrix. Now what we don't want to do is to build an inertial unit, so it's some kind of box inside the vehicle which takes into account some inertial measurements. What I call inertial measurements is some acceleration, A, but that are expressed in R1. So I will call it R1, so it corresponds to some acceleration. And also some rotation vector, omega r, which can be obtained by gyroscope. So gyroscope. And from these quantities, I want to know where I am. So to compute the pose of the vehicle. So it means the pose, it corresponds to the position, which belongs to R3. So it can be, for instance, this point, the center P, the center of the robot frame. I want also to know, for instance, the speed, which I cannot measure directly, expressed in the robot frame, for instance, which also belongs to R3. I want also to estimate the orientation of my vehicle, so phi, theta, and psi. So from this, I want to estimate these quantities. And this is the role of the inertial unit. To do this, I will take all the vector P, VR, and the Euler angle, and I will build a vector named X, and if this one I call it U, I will try to write this system into this form, X and U. This one is measured. This one I know the initial state. I assume I know the initial state. And using an integration method such as the Euler method or Runge-Kutta method, I will be able to integrate this equation and to have a solution x of t, so it will be an approximation, and x of t will correspond to the trajectory of the vehicle, not only in R3 but also I will know its speed and its orientation. So to have this, I will have to write P dot, to write VR dot, and to write phi dot, theta dot, and psi dot. All this with respect to itself, so P, VR, phi, theta, and psi, but also with respect to AR and omega r. So I will start with this one. So I know first that P is the position of the vehicle. P dot is, since I'm able to go from one frame to another using a rotation matrix R of phi, theta, and psi, P dot is equal to R of phi, theta, and psi. So this one I will call it for simplicity R, multiplied by VR. So this will correspond to my first equation, my first state equation. So I will need this one. Now I will have to do the same with this one also. So this one has been done. Now with this one. So I will compute the derivative of the previous equation. I will get p dot dot equal to, so this one is RVR. So I will the derivative is R dot VR plus R VR dot. Then I will isolate this one because it will correspond. It's what the one I want to isolate in the state equation. And if I do this, I will obtain VR dot equal, so it will be R transpose, because the inverse of R is R transpose, P dot dot, so this one, minus R transpose R VR VR dot, right? This corresponds to the acceleration expressed in the R frame, in the robot frame. So I'm allowed to use it since I measure it using accelerometers. And this one corresponds to omega R to this matrix. Okay. So I have my second equation. My first equation was this one. My second equation is this one. Now, what remains me to do is to compute the state equation associated to the Euler angles. I know that omega expressed in R0, so I will call it omega 0, or omega expressed in R0, is equal to R of phi theta psi multiplied by omega in expressed in R1. I have already proved that omega expressed in R0 can be expressed in a linear way using a matrix multiplied by the derivative of the Euler angle. Where here I have some theta, some psi, and some phi. Thus, if I develop this, I will obtain this matrix was this one. Now what I want to do is to isolate this one. So I will isolate this one. This one I know its expression with respect to phi t times c. So what I will do, I will inverse this matrix, so power minus 1. So, and I will multiply by the Euler matrix. If I do this, I will obtain phi dot theta dot psi dot is equal to matrix multiply by omega expressed in R. It's what I call omega R expressed in the robot frame. This matrix will have the following form: 1, 0, 0. So if I compute this, I will not do it here. Tangent theta multiplied by sine phi. Here, tangent theta cos phi. Cos phi minus sine phi. sine phi divided by cos theta and cos phi divided by cos theta. So what we have shown here is that from a cinematical point of view, our vehicle behave obeying the following state equation with an input the acceleration AR and the rotation vector omega r expressed in the vehicle frame. And from this, if I integrate this equation, I am able to get P VR phi t times c. To do this, I need to assume that the initialization is perfect. For instance, I know all these code x, I know x at time t equals 0. But I need to measure this for all time. So when I am in an inertial system, I need a box, so everything inside a box. So I will draw here the box without any other interaction with the environment. I mean, there is no cameras, no sonars, no radars and so on, no exteroceptive system, no exteroceptive. So I mean that everything I should be able to put inside the box which is inside the vehicle. So for instance, it can be a system with spring like this, with a mass here, and when the robot will accelerate in one direction, for instance in this direction, then the mass will move here, and I will be able to observe this inside the box. Also, when so this will correspond to a measurements of AR. Moreover, when my robot or my vehicle is turning like this, rotates, then my mass will also rotate, and I will be able to see it. So from this rotation, I will be able to measure omega r expressed in the robot frame. Now from this, I integrate using a Runge-Kutta method, for instance, to get all these quantities. All the reasoning that has been done here is without the gravity. So far from the Earth, and now in practice I have some gravity field, and I have to take it into account. When I have the gravity, things are a little bit different. For instance, assume that I am on the Earth, and I put my box here. It doesn't move. So the gravity is oriented downward, and I will feel an acceleration. I will measure an acceleration like this, a measure. Whereas there is no acceleration, and what I measure is the opposite of the gravity. So in general, I can say that so the other situation I can describe is the following. I have a box, and this box is falling down. So like this. So of course, I will feel an acceleration downward. I will feel no acceleration. I am in practice accelerating downward, but what I measure is equal to 0. But the acceleration I actually have, I assume that there is no friction with the air. The acceleration I have in reality corresponds to the gravity. So it's easy to understand what I measure. A measure corresponds to AR minus the gravity, but the gravity should be expressed, so here it is, should be expressed in the box frame. So R transpose of J multiplied by J, so the gravity vector. Thus, in the inertial unit, if I want to take into account the gravity, I should replace this one, AR, by R transpose of phi theta psi multiply by the gravity where I am. Okay, so the new, if I do this and plus A measured in my frame. So now, if I replace this by this, I will obtain as a new input not the true acceleration I should have measured without the gravity, but now the new input is AR measured. So I said previously, my inertial unit taking into account the gravity J as a new input AR measured, and also the rotation measured by a gyroscope omega r. So what is important to have is inside the memory of the inertial unit, I need to have a map of G. So it means that I know my environment. My environment can be, for instance, the Earth, like this, the Moon here, or whatever. And I know that if I am here, the gravity will be like this, J of P. Can be like this, like this, like this, or whatever. So I need to know my environment. It might be also interesting, so this corresponds to the notion of map, of the gravity map of the environment. If I am under the water, also, assume that I have a surface of the water, I know that I have some kind of underwater mountains like this. I have some ideas of the gravities, so it's like this, but here I am attracted by the mountains. If I have this kind of information, I can improve the improve the behavior of the inertial unit. Now, sometimes I have also some exteroceptive measurement using cameras and so on. So I can sometimes measure my speed, and a fusion can be used to improve the accuracy using a Kalman filter. So Kalman, if I want to make the fusion with other exteroceptive measurements. And the last thing, if I want to stay purely inertial, then it might be interesting sometime to have two inertial units. For instance, I want to explain, if I have some kind of, I want a box, recall that before I explained that I have a mass m with some springs like this and so on. But it may be interesting sometime to have also another mass. So I put also another mass, m2, and we can understand that the information given by one mass or another are strictly the same when J of P is constant. But it is not always the case. For instance, assume that I am on the Earth, like this. I have here my big box. I do not see anything except feeling some acceleration. And if I am a mass here, m1 and m2, assume that the box is falling down like this. Then, since the gravity here, J of P2, is larger than J of P1, the distance, so if I have no spring, the acceleration of this one will be larger, and the distance will increase, the distance between the two of them. Of course, if I have springs, I will be able to see the spring moving and to measure the fact that J of P1 is not equal to J of P2. This can be used to improve my localization also. Note that the inertial unit I have described previously does not use any mass or inertial matrix and so on. It assumes that I am able to measure AR and omega R with very good accuracy, which is the case if I take some expensive inertial system. Now for small robots, for instance a submarine or whatever, I draw here some kind of vehicle. This vehicle may have some propellers, for instance, or some other actuators which makes it possible to move, and these actuators exert some forces in the system, for instance F1 and F2, and these forces F will translate into some acceleration, A, directly expressed in the robot frame, AR, and also will rotate it with omega R. So there is a direct relation between the forces and the input coefficient. So sometimes it's important to, I will not have some expensive sensors to have this, but I will measure directly these forces and translate it into some acceleration or some rotation. This can be done, for instance, using two important laws. The first one is the Newton law. So the Newton law is m, the derivative p dot, equal to the forces. So I can express the Newton law in the robot frame. Let's say AR equal to the forces expressed in the robot frame, like this. And for the rotation, if I express in the robot frame, I will obtain something similar, which is called the Euler rotation equation, where this one is a Newton equation. So the Euler rotation is the identity, no, not the identity, the inertial matrix, derivative of omega r plus cross product omega r and inertial matrix omega r is equal to tau r, where tau corresponds to the torque expressed also in the robot frame. So in practice, the Euler equation usually is the Euler second law, states that in the initial frame, the time derivative of the angular momentum is equal to the applied torque. So how can be obtained this? So what the derivative of r I omega r is equal to R to R. So it's what I said, that it is the Euler second law. The time derivative of the angular momentum is equal to the applied torque. So from this equation, I obtain R dot I omega R plus R E omega R dot is equal to R to R. Now, this is equivalent, so I will isolate this one, and I will obtain R transpose R dot I omega R plus I omega R dot is equal to the torque. This corresponds to the cross product by omega R, and this equation now corresponds to the Euler rotation equation. Okay, so now I have these two rules that will allow me to transform some forces and some torques into some acceleration and some rotation in order to apply my inertial unit system.